Okay, so we looked at finding the eigenvalues in the eigenvalue problem, and I want to look at the associated eigenvectors. And so just remember, we're talking about the system, or the equation here, if you will. X equal lambda. X, lambda is a scalar, so that's the eigenvalue, and then x is the associated eigenvector. And remember, we transformed that into the following. Okay, and we talked about solving this, and of course we wanted the eigenvectors x to be non-zero. Obviously, if x were 0, then this equation would be true regardless of the value of a or lambda, and any value of a or lambda would work. And so we're looking for the non-trivial solutions, which for the eigenvalues then require this matrix lambda I minus a to be singular, and we found the eigenvalues by setting the determinant of this matrix equal to 0 and solving for lambda. Now, the set of all the eigenvectors corresponding to a given eigenvalue lambda, right, together with the 0 vector must form a vector space. So why is that? Why must they form a vector space? Well, if you look at this, the x's are what we're looking for. And remember we said the non-zero one, so of course I'm throwing in the 0 vector, which is a solution to this equation. However, the eigenvectors were the non-zero solutions. But what is the set of all possible solutions then to this system? What is all the set of all solutions to lambda I minus a times x equals 0? Answer, that's the null space of lambda I minus a. Right, so that's why the reason why they are a vector space is that's exactly why they are the null space of lambda I minus a. And so the set of all eigenvectors together with the 0 vector form a vector space. So we need to give it a name. It's the null space of lambda I minus a. We could call it that, but we want a better name. And so here it is, the solution space of lambda I minus a x equals 0 is called the eigenspace of a, corresponding to lambda. So that's a pretty cool name, huh? Eigenspace. See, we're learning all sorts of neat words we can impress our friends with. Okay. More than that, though, again, we want to be able to find these vectors, but when we talk about these vectors forming an eigenspace, we're more interested in what? Finding a basis for, and then, of course, the corresponding dimension of the eigenspace. And that's what we're going to do. Once we find the basis for the eigenspace, I can find any eigenvector in that set. And so that's how we're going to proceed. So let's go back to this problem here. In the last video, if you recall, we found the eigenvalues. The eigenvalues for this matrix were -7 and 5. You can look at the last video for that. All right. So let's find the basis for the eigenspace corresponding. Let's start with lambda equal -7. So there's an eigenspace, a vector space, for each of these two eigenvalues. So if you remember, lambda I minus a, what's that going to be? Well, you can construct that. Let me just go back a couple pages from our previous video. And in the previous video, we found lambda I minus a. It's right here. So all I'm going to do is simply replace lambda with -7. Replace lambda, so I'm going to get -7 minus 1. I'll have -8 here. -7 plus 3 is -4. So if I plug that in, I get -8, 8, 4, and -4. Okay. Now, I am solving this system, so keep in mind this is the coefficient matrix for the system. I'm not going to usually make the augmented matrix because we know there's zeros here. But you've got to remember these are the constants. These are the coefficients in here. I'm going to put this into reduced echelon form to solve, and I think you can do that without a calculator. Look at this. You see something interesting about the rows? They're in proportion to one another, for instance. So if I do, for instance, 1/2 row 1 and add it to row 2, what's going to happen? 1/2 row 1 added to row 2, I'm going to get zeros here. And then divide, or multiply rather, row 1 by negative 1/8. And your end result is the following. Okay, so there's, and don't forget we've got the zeros out here, right? These are coming from the constants, right? The coefficient matrix. And coefficient matrix is this, and our coefficients are x1 and x2. Well, notice I have only one leading one, and so x2 is a parameter, as indeed we should have a parameter, right? Because again, we are looking for the non-trivial solutions to this system. If you end up with the identity matrix here, right, for the reduced echelon form, that means your original matrix was invertible, which means this system has only the trivial solution, which means you've messed up. All right, you can't have that situation. Mainly the way you mess up in this one, I found to students, if you go back to the last video, when you're subtracting the A, they just forget to subtract the sign numbers. And this, you know, becomes -8, and this becomes -4, or something like that. You get something wrong, and then you end up with the identity matrix here. So if you get the identity matrix here, make a mental note, something is wrong. That is incorrect, because that would say the solution is what? Only x1 and x2 both equaling 0, meaning only the trivial solution. And that's not the case, right? We've set it up so that we have non-trivial solutions. Okay, so from the first equation here, I have x1 minus x2 equals 0. So x1 is equal to x2, which is of course the same as t, right? And so our solutions, x1 comma x2, are just what? T comma t, right? Because x1 is t and x2 is t. Or what? T times the vector 1 comma 1. So this vector here, it spans the eigenspace, because every vector in the eigenspace, every vector in this vector space can be written as a scalar multiple of this one vector. It's a linear combination of one vector, right? And it's clearly linearly independent because it's the non-zero vector. And so there we have it. There's the basis. This one vector forms a basis for the eigenspace of A, corresponding to lambda equal -7. Right. Now, of course, what's the dimension of this vector space? Obviously 1. Notice it's a subspace of 2 space. 2 space can have what? Only 3 possibilities for a subspace of 3 space. Subspace of 2 space. All of 2 space, the 0 vector space, or what? Any line passing through the origin. What's this geometrically? A line passing through the origin, right? Dimension is 1. All right, let's just find the other eigenspace basis for that. This was lambda equal 5 was the other case. And so in this case, if you look at lambda I minus A, you get the following. And I think you need to make sure you confirm that that's what you get. When I look at the reduced row echelon form for that, pretty easy to see what you're going to get here. I think you can do that without even a calculator in 2 row operations, right? Take -1 row 1 added to row 2, and then multiply row 1 by 1/4. Okay. So again, there's my leading one. Again, x sub 2 is a free variable. And this first equation is x sub 1 plus 2 x sub 2 equals 0. Now, where did that 0 come from? Remember, I'm not writing my constants out. I'm just looking at the coefficient matrix. So keep that in mind. There's still zeros there in the augmented matrix. So x1 is -2x2 or -2t. And so what do we get for our Vector x is x1, which is negative 2t, x2, which is t, or t times the vector negative 2, 1. So this vector forms a basis. For lambda equal 5. Now again, this is not unique, right? In fact, any non-zero scalar multiple of this vector, say negative 4 comma 2, or 1 comma negative a half, etc. Any scalar multiple of this vector here is also a basis for the eigenspace of A corresponding to lambda equal 5. Notice the dimension there is also 1. Okay. Well, that was for the 2 by 2 case. Let's move on to the 3 by 3 case. So hopefully you looked at the video previous to this. Again, we solved the eigenvalue problem for here. So I'll just say recall from that. We found lambda to be 1 and 2. And so I want to take a look for lambda equal 1. What happens there? I take a look at lambda I minus A. Okay. If you do that, I want you to confirm that you get this matrix here. Just emphasize again, we'll go back and see where in the last video we found this lambda I minus A. Here it is. All I'm doing is replacing lambda with 1. Right, so 1 minus 2 is negative 1, 1 minus 3 is negative 2. So I'm getting those values there. All right, so now I'm going to put this in reducer echelon form. And you can actually use a calculator to do this. It's not real hard actually to get this in reducer echelon form in just actually a couple of row operations. Okay, there's my leading ones. Don't forget this is the coefficient matrix. I've still got zeros here. Notice here I've got x3 is a parameter. We'll call that t. And my first equation says x1 plus 2x3 equals 0. And so what do I know? x1 is negative 2x3 or negative 2t. And this right here says what? It says x2 minus x3 equals 0, or x2 is equal to x3, which is t. And so x1 is negative 2t, x2 is t, x3 is t. So it's any scalar multiple of this vector here. So the basis for the eigenspace corresponding to lambda equal 1 is this. I'll let you fill in all the words there, right? But that's the basis for the eigenspace of A corresponding to lambda equal 1. Again, what's the dimension of this? The dimension is 1. Let's look at for lambda equal 2. Seems like all our examples we've had a basis with just one vector. Found dimension 1 vector spaces. Is that always the case? No. Let's take a look at this case, right? Lambda I minus A. In this case, if I replace lambda equal 2 in that, I get the following. And I bet you can find that reducer echelon form almost by yourself with 3 row operations real quick. Multiply the first row by half, and then add the first row to the second row, add the first row to the third row, and you're going to end up with this, the reducer echelon form. Okay. Here's my leading one. Notice there's no leading one here. X sub 2 is a parameter, I'll call that R, and X sub 3 has no leading one, it's a parameter. And what's this equation say? X sub 1 plus 0 X sub 2 plus X sub 3 is equal to 0. Remember, the zeros are here. I'm not putting the constants out there. This is the coefficient matrix. Don't say this is x1 equals 1. This is x1 plus x3 equals 0. So x1 is equal to negative x sub 3, which I'm calling t. And so my solution x is of this form. x1 is negative t, x2 is r, x3 is t. Well, we've seen this sort of thing. Remember, all we're really finding is the basis for a null space. If you keep in mind, this is the basis for a null space. Lambda I minus a x equal what? 0. And so we've seen stuff like this when we're finding null spaces. How do we do this? Break it up this way. Hopefully everyone understands again what I've done here, but now every vector in my eigenspace can be written as a linear combination of these two vectors. Therefore, these two vectors span the space, and they're clearly linearly independent. And so, basis is the set of these two vectors. This is the basis for the eigenspace of A corresponding to lambda equal 2. And notice the dimension is 2 because there's two vectors in the basis for this vector space. Now, I just want to make one little note about this. Again, we're just looking at the computation of it, finding eigenvalues and how to find the corresponding eigenvectors. That's the important thing in this section. I will say, if we go back to when we found the eigenvalues for this particular matrix here, we went back to find the eigenvalues in this process. Remember, notice that we had 2. It was a degree 3 polynomial, and but we only had 2 zeros because one of the zeros, the 2, the eigenvalue 2, was of multiplicity 2, right? And sometimes when we talk about eigenvalues, we talk about their algebraic multiplicity. Here's the algebraic multiplicity for the eigenvalue 2. Lambda equal 2 has a multiplicity 2 because there's 2 lambda minus 2 factors. 1 has only one factor, lambda minus 1 factor, so it's multiplicity 1. So does the algebraic multiplicity have anything to do with the corresponding dimension of the eigenspace, which is something we actually sometimes call the geometric multiplicity? Well, notice for lambda equal 1, right? And lambda equal 1 was a algebraic multiplicity 1. Its dimension of its corresponding eigenspace was 1. And for 2, which is algebraic multiplicity 2, it has a subspace of dimension 2. Well, here's the answer to that question. Is that always the case? So if I have a algebraic multiplicity of k, let's say, is the dimension of the corresponding eigenspace going to be k? And the answer is not necessarily. If you have an algebraic multiplicity of k, the dimension of your eigenspace is at most k. Is at most k. So if you have a multiplicity 2 eigenvalue, algebraic multiplicity 2, its dimension of its eigenspace could be 2 or 1. 2 or 1. Okay. Well, I want to just close then this section off with a summary and then an important relationship that we're going to prove between eigenvalues and, since we've been talking about n by n matrices, what if A is invertible? Is there anything that we can say about its corresponding eigenvalues? So first of all, just a summary, if A is an n by n matrix, the following statements are equivalent. Lambda is an eigenvalue of A. Lambda is a solution to the characteristic equation, the determinant of lambda I minus A equals 0. Right, and that's exactly how we found the eigenvalues in practice. The system of linear equations here has non-trivial solutions. Remember, that's what forced this issue, so that this matrix here, the coefficient matrix, was singular. And also, what is equivalent? There is a non-zero vector x such that ax equal lambda x. In fact, this is the problem we started with. So these are all equivalent ways of saying the same problem, and we are using obviously different parts of this in solving for the eigenvalues. And I hinted at this before too. We can also extend the definition of eigenvalues to linear operators. So if we have a linear operator T which goes from vector space V codomain, domain of V to a codomain of V, right, that linear operator, then any non-zero vector x is called an eigenvector if t of x is a scalar multiple of x. So if t of x is lambda times x. And of course, right, when we think about t of x, that is what? A times x, right? If it's a matrix transformation. And so, this is just extending it to a matrix operator. Now, let's take a look at the relationship between eigenvalues and the invertibility of a matrix. Take a little time to spend on this. This is important here. So guess what? Remember that long list of equivalent statements? We're going to add another one. And that is, if you have a square matrix A that's invertible, that's going to be true if and only if what? Lambda equals 0 is not an eigenvalue of A. Now some of you might be saying, hey, I thought we were forcing the coefficient matrix to be singular. Go back up here, right? That's lambda I minus A is singular. Right? That doesn't mean A has to be singular. So A could be singular or invertible. But the question is, if A is invertible, what can we say about its eigenvalues? And it turns out this is what we can say. If it's invertible, lambda equals 0 is not an eigenvalue of A. Which of course means if A is singular, then what? Lambda equals 0 must be an eigenvalue of A. Okay, so the proof goes like this. Let's let A be n by n. Right. And then I want to look at the characteristic equation. And remember, it's a polynomial in the variable lambda, right? And we looked at some examples here, right? Here was the characteristic polynomial in this case for a 2 by 2. The characteristic polynomial for a 3 by 3 was here in factored form. Of course, if I expand all this out, what's the highest degree term going to be here? Lambda cubed, right? So in general, if it's n by n, the characteristic polynomial, which of course is determined by the determinant of lambda I minus A, equation, we'd be setting that equal to 0, sorry. Characteristic equation is just setting that characteristic polynomial equal to 0. And what's that going to look like? Well, the characteristic polynomial is going to be lambda to the n in this case, right? Plus what? Some value lambda n minus 1, right, all the way down to Cn minus 1 lambda plus Cn, that's the constant term, equals 0, right? This indeed, again, is the determinant of lambda I minus A. And again, these coefficients, C1, C2, all the way down to the constant, depends on the matrix A, right? Depends on the matrix A. But I want you to note, first off, that lambda equals 0 is a solution to this equation if and only if, the only way that lambda equals 0 is a solution to this equation is true if and only if what? Cn, the constant term, must be 0, right? So if I plug in lambda equals 0, all these terms go to 0, which leaves me what? Cn must be 0, right? So if Cn is not 0, then lambda equals 0 is not a solution to that equation. Okay, also note if, again, lambda equals 0, then the determinant of lambda I minus a equals what? Well, if I plug in lambda equals 0, this characteristic polynomial here becomes just what? All these terms go 0. It's just Cn. Right? Just Cn. But lambda, right, is equal to 0, and I'm going to, of course, replace 0, lambda with 0 here. 0 times I is just the 0 matrix. The 0 matrix minus a is -1 times a. Okay? And then I'm going to hopefully help you remember what we talked about back in chapter 2 about determinants. Okay? So the determinant of negative a is some quantity times the determinant of a. Okay? Determinant of negative a is some quantity times the determinant of a. So what goes here? What goes here? You know what goes here. Well, if you said -1 to the n power, then you get a big prize. A virtual pat on the back from over the internet. There you go. Pat on the back. There it is. I hope you remember where this comes from, because a is n by n, right? And -1 times a is what? Multiply every row by a by -1. And each time I multiply a row by -1, a row of a, then the determinant of that new matrix is -1 times the determinant of a. Since I've done that n times, right, this is what it is. So if you said just -1, you were not right. Okay? Depends on the value of n. If n is even, it's +1. But the bottom line is I want you to focus on is that this is clearly not equal to 0. It's either +1 or -1. Okay? And so, with this final statement, I will simply say that the determinant of a equals 0, the determinant of a is equal to 0, if and only if Cn is equal to 0, right? If Cn is 0, then the determinant of a has to be 0. If the determinant of a is 0, then Cn has to be 0, because this quantity is not 0. But Cn is equal to 0 if and only if what? Lambda equals 0. The eigenvalue is equal to 0. And that's really the proof. Because what do we know if determinant of a is equal to 0? That means a is what? Singular. So a is singular if and only if lambda equals 0. Right? And therefore, lambda equals 0 is not the eigenvalue of a, right, if and only if a is what? Invertible. So we kind of got the statement for if a is singular, what must be true. Right? Lambda equals 0 has to be an eigenvalue if a is singular. Right? Let's just emphasize a is singular. Okay? And otherwise, then we have, right, if a is not singular, then this statement is true. So, this will be the final time we'll look at this theorem. I want you to take a look in your book, if you have it, at section 5.1, which is where we're talking about the eigenvalue problem. And at the end of that section, you will see on page 299 the list of equivalent statements for a matrix A that's n by n being invertible, right? First statement is A is invertible, and so here's our long list. We've looked at all of these, right? All the way down, right? And in fact, we got down to T down here, and now U, right? A is invertible if and only if what? Lambda equals 0 is not an eigenvalue of A. Okay. We're running out of letters in the alphabet, so I hope we're close to being done. Okay. And we are. This will be essentially the last time we expend this. There are some other statements we could add, but we're going to stop right here. So here's all the equivalent statements to an n by n matrix being invertible. Here they all are. Okay, so in the next video we are going to take a look at the idea of similar matrices and then talk about a process called diagonalization, and it uses the ideas we developed here with the eigenvalues and the eigenvectors.